Good morning, good afternoon, and good evening, and welcome to today's webinar on ionic liquid GC phases, a valuable asset in the GC toolbox. I'm Len Sadisky, R&D Manager for Gas Separations at MilliporeSigma. MilliporeSigma is the life science business of Merck KGaA, Darmstadt, Germany, in the United States and Canada. The agenda for today's webinar will include a brief introduction and history, an overview of ionic liquids. We're going to talk about the phases we've developed, talk about water call, talk about the I series of ionic liquid phases, and do a GC-MS bleed comparison, and then a summary of our presentation. Ionic liquids really aren't that new. They've been around since 1914, when Walden discovered the very first one, ethyl ammonium nitrate, which was found to have a melting point of 12 degrees C. This was found in St. Petersburg, Russia. And then, in the mid-1990s, Dan Armstrong and his group, late 1990s, began experimenting looking at ionic liquid type stationary phases for gas chromatography. And you can see his very first one of the very first ones that Dan's group looked at was butyl-methylimidazolium with the PF6 anion. And so this is some of the very first work they published at seeing the kind of unique selectivity of the ionic liquid stationary phases. They then did additional work with these phases, along with Jared Anderson and a few other people, where they characterized the ionic liquids looking at the Abraham solvation parameters and noticing that the ionic liquid phases offered many solvent interactions, more than any other type of stationary phase currently available. So what they started doing, first of all, in their studies where they were looking at monocationic ionic liquid phases, and the group started adding bulkier side groups to the ionic liquid, to the cation, to see if it changed the stability or selectivity of the stationary phase, and they found that it did improve the overall quality of the phase. So then they began looking at dicationic and tricationic ionic liquid type stationary phases. So you can see some examples here of some imidazolium-based dicationics and pyrrolidinium-based dicationic ionic liquid phases. So, as I was saying, the prior work with Dan's group focused on monocationic ionic liquids, but again, they did not exhibit the predicted chromatographic benefits. Essentially, they were acting almost like liquid crystal phases, where liquid crystal phases offer some very unique selectivity, but they have a fairly limited working range. So within that predicted working range, they'll work very well. But once they get out of that working range, they begin to lose their efficiency and their selectivity. So again, then Dan's group start making dicat and polycationic ionic liquids, and then they showed some very predictable chromatographic benefits. And this is one of the first papers that we published with Dan's group in LCGC back in August of 2009, called The Advent and Potential Impact of Ionic Liquid Stationary Phases in GC and GC times GC. So what makes ionic liquid stationary phases so desirable? First of all, they remain liquid over a wide temperature range, room temperature to 350 plus degrees. Remember, we want to do gas-liquid chromatography, so we need to have these phases in the liquid range, rather than being gas-solid chromatography, which is an entirely different type of chromatographic kinetics involved in the processing. The phases have very low volatility. They're typically highly polar in nature. As I said earlier, they have the broadest range of solvation interactions of any known solvent, good thermal stability, high viscosity. Now that means something to me as a column manufacturer. I need to have a fairly viscous material to be able to put down a good stable coating of the stationary phase. And again, if you have a good synthetic organic chemist, you can easily tailor to provide different selectivities or polarities for the ionic liquid stationary phases. Here's an example of the very first ionic liquid stationary phase that we commercialized, what we now call the SLBIL100. I'll give you a little bit of history on why that name came up. First of all, you can see it's a dicationic imidazolium-based ionic liquid phase with a vinyl group as the substituent on the imidazolium. There's a C9 linkage chain, which is very important in the overall selectivity of the stationary phase. And then, of course, we have the different cations. In this particular case, we're showing the NTF2 cation, which is probably the most widely used cation for the ionic liquid phases. And another one that's commonly used is shown on the bottom right of my slide, the triflate anion. So those are the two most common. We've been experimenting with a number of different anions to see what kind of stabilities we can get for the stationary phases. So as you can see, there's numerous combinations of cations and anions are possible, again, to tailor the selectivity, application, or function. Again, I'm showing you the dicationic, and various pendant groups can be changed to change the overall selectivity. As I'll show you later in the presentation, the difference between IL-100 and what we call SLBI-111 is the vinyl group that is on this particular SLBI-100 is replaced by a methyl group. So it gives it a little bit different character in terms of selectivity. Now, as I said, this was the very first one that we developed, and it was quite interesting. When we start looking at this particular stationary phase, it had a selectivity almost identical to the most polar stationary phase at that particular time, a stationary phase known as TCEP, or tris-cyanoethoxypropane. So we needed to figure out a way of how can we designate these stationary phases relative to traditional phases in terms of where they stand selectivity-wise. So in discussing this with Luigi Mondello, one of our consultants at the University of Messina, we decided to go back to the basics. So Luigi's group basically took all the traditional stationary phases along with the ionic liquids and did some fundamental gas chromatography by looking at the McReynolds constants on these particular phases. And so what he did is he took a summation of the first 5 McReynolds constants, and as I said, because the SLBI-100 was the most polar, or very similar to TCEP, which is the most polar phase, we did a summation of the first 5 McReynolds probes, and then did a division of what the value is for a particular phase over the SLBI-100. So you can see for SLBI-100, the summation is 4,437. If we look at something like the SLBI-60, you can see the value is 2622. So if we do that ratio, it comes out to be about 59. So we name that particular stationary phase SLBIL59. Now this is not something really new. For those of you that have been around for a long time and are familiar with this, a company that used to manufacture capillary columns called Chrompack, they used to have a different designation for their phases, and no one really knew what it meant. Well, when you look at their particular wax phase, they called their wax phase CP-SIL52CB. So if you look at the Sapelka wax phase, you can see when we do the polarity number, it is 52. So that gives some validity to our nomenclature system for how we're developing or naming the ionic liquid stationary phases. So to show you where they stand relative to traditional phases, on the left are your traditional phases going from the very nonpolar phase like the SPB octal up to TCEP, along with the maximum temperature for those phases. On the right are the ionic liquid phases, and you can see the ionic liquid phases fall into the polar, highly polar, and extremely polar range. One other thing to note is that all of the ionic liquid phases have maximum temperatures very similar or even higher than the particular traditional stationary phase of a similar polarity. So the interesting thing is looking at the SLBIL 61, 61I, 60I, 290 versus 300 versus 280 for something like a Sapelka Wax 10. When you look at the SLBI 111, the most polar phase that we've commercialized, it has a maximum temperature of 270 degrees, which is significantly higher than the 140, 145 degrees C for the TCEP type stationary phases. So let's look at what's been developed. We've got some general application phases along with some special application phases. So under the general application phase, first of all, we have the dicationic phosphonium-based ionic liquids. So we have the SLBL 59, 60, 61. Then we have the tricationic phosphonium-based ionic liquids, which we call SLBIL 76. And then finally getting to the more polar phases, these are the dicationic imidazolium-based ionic liquid phases, the SLBIL 82, IL-100, and IL-111. We've also developed some special applications, in particular the water call, which I'll spend some time on. We actually have 3 phases, but only one of these have been commercialized. There's the water call 1460, the water call 1900, and the water call 1910. And then we also have 2 very special application-specific phases. One we call the SLB-IL-PAH for polynuclear aromatic hydrocarbon analysis, and the SLB-IL-D3606. It's a capillary column designed to meet the requirements of the ASTM D3606 methodology. So what makes these ionic liquid phases so unique? Primarily, it has a very unique selectivity, and they are the only phases capable of performing all 5 of the interaction mechanisms at a single time. So this was some work done by a group in Madrid, Spain, where they've taken 95 probes and looked at 52 different selectivity columns. So what they did is each of these probes looked at a different type of interaction, be it a hydrogen acceptor, hydrogen donor, dipole interactions, pi-pi interactions, or dispersive interactions. So if you look at these particular plots in the principal component analysis, you can see on the bottom left cluster or line 1, those are your extremely nonpolar phases, the polytrifluoropropyloxanes, your methyl silicone type phases. Very distinct line where all those particular phases fall. Line 2 are your phenyl phases, where we've added a little bit more interaction to the stationary phase. By adding the phenyl groups, we start adding some pi-pi type interactions and possible dipole interactions, but mainly pi-pi interactions. So that's line 2. Then you look at line 3, the polysiloxane phases, and again, we're adding more interactions, more dipole type interactions are added. So these stationary phases have more mechanisms. So you can see the 3 distinct patterns. Then finally, or not finally, but the next cluster is the polyethylene glycol phases, and you can see they're very unique compared to your traditional phases. So they fall into their own sector on this principal component analysis. And then finally, the ionic liquid phases. Very unique, very different in terms of selectivity compared to traditional phases like siloxane-based phases and polyethylene glycol-based phases. And again, the way the ionic liquid phases offer their unique selectivity, they're the only phases capable of simultaneously undergoing hydrogen acceptor, hydrogen donor, dipole interactions, pi-pi interactions, and again, all phases in gas-liquid chromatography have a dispersive interaction to some extent. It's just adding these other mechanisms which makes the unique selectivity of the phases. And again, this was a reference where this was the salvation parameter model was published in the journal Chromatography back in 2014. Now, we said they're very comparable to traditional phases, but there are some differences. And here's an example where we're comparing the SLB-IL-60 to a traditional wax phase. And all we're doing is looking at a standard polar test mix, and you can see the difference in the elution pattern. Peaks 7 and 8 on the SLB-IL-60 elute in a different pattern compared to your traditional wax phase. Whereas on the SLB-IL-60, the dimethylphenol comes out prior to the dimethyl-aniline peak, and that is reserved on the wax, and it's reverse order on the wax phase. So again, very similar, but there are some differences in selectivity, as I'll show you as we go through this talk. Here's another example. I've done a lot of work in the area of FAME analysis, fatty acid methyl esters, and here we show the separation of some monoionic fatty acid methyl esters on the SLB-IL-60I versus a traditional PEG phase. So if you look at this methyl oleate and methyl elidate on the SLB-IL-60I, the trans isomer elutes prior to the cis isomer. On a traditional PEG phase, when they do separate, you always have the cis isomer coming out prior to the trans isomer. Again, part of this increased dipole-dipole interaction that the IL-60 phase has compared to the PEG phase, because when you think about a PEG phase, what interactions do they have? They've got a dispersive interaction, they've got hydrogen bonding, and then depending upon the character, either an acid or base interaction. So there's very limited interactions on the PEG phase, whereas the SLB-IL-60 has these increased interactions. And we see the same effect with the diionic fatty acid methyl esters, where we're looking at on the SLB-IL-60I, the trans isomers elute first, followed by the peak in the middle, which is the cis-trans and trans-cis group, and then finally the cis-cis group. In comparison, on the PEG phase, it's the opposite order, where the cis-cis group comes first, followed by the trans-trans, and then finally by the cis-trans, trans-cis group. So again, the increased interaction mechanism of the ionic liquid phases offers the unique selectivity. And in fact, that particular selectivity makes the wax phase almost look like a highly polar cyanosilicone in the elution pattern of the fatty acid methyl esters. Here's another example which is quite interesting. Again, comparing the wax phase to the SLBIL60I using a 37-component FAME mix we developed a number of years ago, which mimics the fatty acid composition of many, many materials, ranging from dairy all the way up to highly polyunsaturated fish oils to polyunsaturated vegetable oils. So looking at the elution pattern, you can see, as I discussed in notes 1 and 2, the difference in the elution pattern in the cis and trans isomers. But then what's very interesting on the ionic liquid phase is that the omega-3 fatty acids elute prior to the omega-6, which is the opposite on your traditional wax phase. And then also, quite interesting, you have the C22, 6, and 3 dosohexaenoic fatty acid eluting prior to something with 5 double bonds. So there has to be some type of shape selectivity going on with the SLBIL60I that allows you to elute something with 6 double bonds prior to something with 5 double bonds. And again, it's totally different elution pattern when you look at that on your traditional wax phase. And again, note a much shorter analysis time. Though we have a slightly thinner film with the ionic liquid phase, it's still a pretty significant reduction in the analysis time using the ionic liquid phase compared to your wax phase. Here's another example where we demonstrate the effect of selectivity of the ionic liquid phases as we go from the least polar, which is the SLBIL59, to the most polar. And what we traditionally do is we use rapeseed oil FAMEs as a marker because it contains a C18-3 fatty acid methyl ester, the C20 saturate, and the C20 with 1 double bond. And as we increase the selectivity of the stationary phase, or the polarity of the phase, you can see that the retention time, again, these columns were all made 30 meter 0.25 millimeter ID by 0.2 micron film, all run at 180 degrees isothermal, identical conditions. And you can see as we go from the SLBIL59, we start reducing the analysis time. But then once we get to around the SLBIL82 phase, we start to see a shifting where now the C20 saturated FAME is eluting prior to the C18-3. As we go to the SLBIL100, the 18-3 peak actually elutes after the C20 with 1 double bond. And then when we get to the extremely polar SLBI111, we now have the C20 saturated fatty acid methyl ester eluting prior to the C18-2 fatty acid methyl ester, and the C18-3 moving well downstream, almost co-eluting with the C22 saturated fatty acid under these particular conditions. Another way of looking at this in comparison to the chromatograms is to calculate the equivalent chain length values. Essentially, they're a type of retention index system based on the fatty acid methyl esters. Same as it's very similar to a COVAT system where you use alkanes. In this one, we're using the saturated fatty acid methyl ester. And you can see as we go from, looking at C18-3 and 6, with the SLBIL59, we have an ECL value of 19.03, indicating that on a log scale, the C18-3 fatty acid methyl ester will elute halfway between C18 and C20 FAME. As I said, with the SLBI111I, when we get down there, we now have a co-elution with the C22. That's how far we have shifted the C18-3 fatty acid methyl ester downstream due to the increased selectivity of that particular stationary phase. Here's some examples. Again, we originally developed what we call the SP2560 column back in 1984 with Dave Firestone of the FDA, and it's been the column of choice for doing the analysis of fatty acid methyl esters, partially hydrogenated vegetable oils, and cis-trans positional geometric FAME isomers. So this is quite an interesting chromatogram where we're comparing the SP2560 with the SLBI111. And this is a composite chromatogram. We actually have a few things going on. The total chromatogram is on the bottom part of the slide, where we have the partially hydrogenated vegetable oil. The top two is where we've done some silver ion solid phase extraction and separated out the trans fraction from the cis fraction, so we can see the difference in selectivity or difference in the elution pattern between the SLBI-111 and the SP2560. And as you can see, it's fairly complementary in terms of the selectivity. Again, the SP2560 has been the standard column since 1984 for performing this analysis, but we believe the SLBI-111, with its unique selectivity, does offer some potential differences and can be used as a complementary column for the separation of these fatty acid methyl esters or positional geometric FAME isomers. A little bit closer, where we're going in and optimizing and actually looking at a 200-meter column to improve the separation, and you can see at the very bottom chromatogram where we've optimized the separation using 150 degrees, a slightly lower temperature, we can resolve almost all of the positional geometric C18-1 FAME isomers on the 200-meter SLBI-111I. Okay, shifting gears. Let's look at some ionic liquid columns for special applications. I want to talk about what we call the water column. It's a column designed to analyze water. It produces a sharp peak shape for water and many other small polar analytes. The water peak is sharp enough so that it can be integrated and quantified, and water does not interfere chromatographically with many other small polar analytes. So we offer three different chemistries, or have offered three different chemistries. Right now, the only one that's commercialized is a water called 1910. And just to give you some background on what these numbers mean, what we've done is we determined the Kovat's retention index value of water at 100 degrees C on each of these three particular stationary phases. So for the water call 1460 at 100 degrees C, water will elute after a C18 or a C14 alkane. On the water call 1900, very close to the C19 alkane, and then on water call 1910, it actually elutes after the C19 alkane. And here's the structures of these three particular water call stationary phases. Very different than the traditional ionic phases I showed you earlier. Again, the water call 1460 is very identical with the cation structure to the SLBIL72, except in this case we've used the triflate anion. Water call 1900 is a monomethyl substituted imidazolium, and as you can see, it has a PEG linker chain, which gives it some unique selectivity towards water. And then, of course, the water call 1910 has a hydroxyethyl substitution on the imidazolium chain, and again, uses the triflate anion to provide the unique selectivity or inertness towards water and these highly polar analytes. Here's an example, comparison of the selectivity of the water call phases. Just noticing how water shifts downstream. And in this case, we're looking at water as an analyte. You can see it on the 1460 elutes around 3 minutes, and it shifted down well past 4 minutes and later eluting compared to the other water call phases. We can also use water as our matrix solvent, and you can see how the very good peak shaped water. Again, this is work done with a thermal conductivity detector, and you can see the shifting of water downstream away from the small polar analytes on the water call 1900 and 1910 compared to the water call 1460. We can look at durability. This is just an example of some work that we've done with the water call 1460, where we just shot water, kept shooting water on the particular columns and looking at the elution pattern, looking for deterioration, and you can see easily 100 analyses. Dan Armstrong's group has reported doing over a couple thousand analyses using water injections on the various water call phases, so they are very stable to water injections. Here's a calibration curve. Again, this is limited because we're working with a thermal conductivity detector, so we can't go to very, very low amounts of water. And you can see here we're linear on the water call 1460 from 0.5% water up to 1% water. We've actually gone up to about 99% water and still see linearity in our responses. Here's what the standard looks like. This is the FID, of course. This is our water standard, 0.25% ethanol in water. And you can see FID on top And then the bottom chromatogram shows the thermal conductivity detector and water eluting well away from the ethanol peak. So you can quantitate both water and ethanol in one analysis. Here's an example of the calibration curve using water with that similar standard on the water call 1910. Again, going from 0.1% all the way up to 0.5% on the water call 1910. Very linear response, 0.9923. So again, we get very good results. And again, we're limited as to how low we can go on this curve due to the thermal conductivity detector. And here's what the standards look like. The 0.05% standard and the 0.5% standard on the water call 1910. Here's an example where we've taken some gasoline and we spiked it with water and trying to find water in this gasoline sample. And the top is the spiked sample using the FID. And then if you look at the bottom chromatogram, you can see the spiked thermal conductivity detector easily detect the water peak at around 9 minutes using the TCD and the water call column. And again, it's eluting in the midst of some of the aromatic fraction of the gasoline sample. Here's where we were looking at a wide variety of solvents, 60 different solvents. Again, the top is the FID, and the bottom is the thermal conductivity detector. And again, you can easily see in the box in the highlighted area where water elutes. Easy to pick out, easy to detect, very easily quantified on the water call 1910. Again, using the thermal conductivity detector. The water call columns can also be used for looking at various alcoholic beverage samples. So here is a sample where we're looking at tequila versus tequila on the FID and tequila on the thermal conductivity detector. Again, with the TCD, we don't get very good response for some of the other organics, but very good response for water and the ethanol peaks, so they can both easily be quantified in the sample of tequila. Here's an example of grappa bassano. I've been lucky enough to be able to travel numerous times to Italy for the International Symposium on Capillary Chromatography, and so I've been able to pick up various samples of grappa. And here we just did a SPME with the carboxyl fiber, and you can see some of the easily quantitate the ethanol. You see some of those bad alcohols, the C4s and C5s, which tend to produce some of the hangover problems, and then you can see the water peak, well resolved, fairly good peak shaping. It was just cut off with the detector, so easily identified and easily quantitated in this grappa bassano sample. Here's a sample of grappino, where we're looking at it on the water call 1910. Again, the same thing. We see a little bit of the C4 and C5 alcohols and some furfural later on eluting, but again, water can be easily quantified along with the ethanol. Here's an example of Tito's vodka. Again, vodka is just supposed to be ethanol and water, and you can see very pure peaks of just ethanol water in this vodka sample. Again, this is an analysis on the water call 1910. Here's an example of ouzo. Again, same type of system that I was running before. You can see the ethanol, the water peaks. You pick up some aromatics, and then you pick a large para-anisole peak, which is very typical of the flavor of an ouzo beverage. So here's some other work that was done in combination with the vacuum ultraviolet detector from VUV Analytics, and this was done by Lindsay Shearer a few years ago, where she was just looking at the amount of water in what was some dry methylene chloride, and she was doing repeat analysis, and you can see she was able, using a series of 11 analyses, where she was doing a minimal detectable level of 13 ppm, excuse me, and her limit of detection was 2.5 ppm. So with this particular detector and using the water call 1910, she's able to get to fairly low limits of water in something like methylene chloride. Now, what's the advantage of the water call and water determination in GC compared to your traditional Karl-Fischer titration? Well, with Karl-Fischer titration, volumetrically, you can go from about 100 ppm to 100% water. With the water call and the thermal conductivity detector, we can go from about 100 ppm to about 100% water. Of course, that's the limitation of the thermal conductivity detector. If we look at coulometric Karl-Fischer, you can go from 1 to 10 ppm up to 5%. And using the water call and the binary discharge ionization detector from Shimadzu, we can go down to that level of 1 to 10 ppm using the water call and the and the BID detector from Shimadzu, and I'll talk about that a little more in the next few slides. Some of the advantages of using GC with the water call over Karl-Fischer titration: no unwanted side reactions, no solubility issues, less hands-on time. Again, you can do both water and the volatiles and semi-volatile material. You have a much lower volume of chemical waste generated. Reduced amount of sample, we can shoot a microliter of sample on the water column and get quantitative results. Less worker exposure to potentially harmful chemicals. And again, the advantage of reduced cost using the GC compared to Karl-Fischer titration. Here's some other examples. We're actually working with Shimadzu with a ASTM method for determining water and liquefied petroleum gas. Current method uses Karl-Fischer titration in the gaseous form. Very difficult to do. You also have some cross-reaction of some of the odorants added to liquefied petroleum gas, for example, propane, with the Karl-Fischer reagents to give you some obscured numbers. So what we've done here, and again, this came from some work that was done on a Shimadzu application sheet, where we're able to do water at 25 ppm easily, and you can see it's well resolved from the propane in the inset chromatogram. Water peak at about 14 minutes. Again, you can see very easily repeatable analysis, very low percent RSD on the column. And our concentration, we Shimadzu determined the percent RSD of 1.76% over 5 analyses on this water peak in this liquefied petroleum gas. Again, these were the conditions, just using the water call with the Shimadzu QP 2010 GC+, 30 meter 0.25, 0.2 micron water call, 55 degrees up to 180 temperature programmed analysis. We looked at here's just an example of looking at reproducibility of the water in liquid propane. This was done on a 30 meter column. Again, this is our initial analysis. Here's our final analysis over 25 analyses. You can see it's very, very stable. Again, the statistics, this is looking at the area counts of water using the BID and the water call 1910 phase. Again, our relative standard deviation is 1.5% over 20 analyses of water in this liquefied propane. Here's some other products, looking at a number of different petroleum products. Work done by Dan Armstrong and his group, Lillian Frink, when she was one of Dan's grad students, looking at a lot of different materials to determine the water content. And here she's comparing headspace gas chromatography versus using the water column. So you can see, ranging from motor oil, number of milligrams of water measured versus the ppm of water, we're down to 770 all the way up to 1630, to 3200 in gun oil, high amounts of water, looking at some crude oil. So it can be used for a wide variety of different petroleum products, again, using headspace, gas chromatography, easily quantitate the amount of water in these liquid petroleum samples. Here's another example, courtesy of Shimadzu, again, looking at water in our gasoline sample. So you can see, using the water column, you can see the water peak is well resolved. It's eluting at about 14 minutes in comparison to some of the aromatics. So you can quantitate both the aromatics and water in a single analysis using the water column in this petrochemical application. Here's an example where we're looking at some other alcohols and where water elutes relative to these compounds. Again, this is using the BID from Shimadzu, the barrier discharge ionization detector, which is about 100 times more sensitive than your typical thermal conductivity detector. So we're at fairly low amounts. And you can see very good resolution of the various alcohol peaks, and water well resolved and easily quantitated. You can even see air peak is detected in this particular sample using the BID. Again, demonstrating its versatility as a universal detector. So now I want to talk about what we call our I series of ionic liquid columns. When we first came out with the ionic liquid columns, we put them out there and let our customers give us feedback in terms of the columns. And one of the comments, we had very unique selectivity with these stationary phases, but they lack a little bit in inertness. So what we did is we went back in and redesigned the surfaces that we coat the ionic liquid phases on to provide better inertness for these phases towards things like alcohols, other reactive type compounds. And we did this with the three most popular ionic liquid phases, the SLBIL60, which became the 60I, the 76I, and then finally the 111I. And here's just some examples, again, comparing it to a wax column. Again, shows both the differences in selectivity and the relative inertness of the 60I versus the wax column. And this is a separation of some fusel oils, active amyl alcohol and isoamyl alcohol, typically two markers in the fermentation process. And you can see very good resolution of these two components on the SLBIL60, very good peak shape, in comparison to the wax columns where they co-elute. And in fact, you'd have to use two different columns to get separation of these compounds on the wax column, whereas the unique selectivity of the SLBIL60I allows us to do it on a single 30-meter column. Again, to compare the selectivity of the three ionic liquid columns, the 60I, the 76I, and the 111I, I just shot the active and isoamyl alcohol relative to some alkane markers. And you can see, again, the effect of selectivity as we go from the SLBIL60, where the alcohols elute after C11, to the 76I, where the alcohols now elute, very good peak shape, after C13. And then with the more polar phase, the SLBI-111I, we now have the alcohols eluting after the C-alkane. So greater retention of these alcohols as you become more polar in the stationary phase relative to the alkanes. We've also found some very good utility for the ionic liquid phases, for example, the SLBIL60I, for doing flavors and fragrances, fragrance allergens. So the next few slides are a series of the allergens, fragrance allergens, analyzed with some mixes that we've developed with our sister company in Books. And here's just some examples looking at the SLBIL60I, what we call mix 1 of the fragrance allergens. Again, these are the allergens that are going to be monitored. And ranging, from things like cyclopropane, terpenes, limenols, linalool, santalol, farnesol, just examples of what's in that particular mix. Here's another series of the particular allergens resolved on the SLBIL60I. Again, just the listing of some of the compounds that are in there, some of these things that need to be monitored. Here's mix 2, again, a wide variety of allergens, well resolved. The 71 allergens, again, we actually looking at the total number of isomers that are available, so we can see they're all fairly well resolved, get a good quantitation of these. We've also looked at some mint oils. Again, mint oils are typically done or analyzed on a wax type selectivity because it gives you very good separation of the particular mint oils. This is an example where we're looking at willamette and peppermint oil on the SLBIL60I. The next shows the same analysis of the willamette and peppermint oil on a wax column. And there are differences in the selectivity of the phase. I'll show you that on the next slide. You can see some of the key components in the willamette peppermint oil comparing the Sapelka Wax 10 and the SLBIL60I. You can see some of the main menthol components, menthol, neomenthol, menthone, well resolved on the SLBIL60I, whereas, for example, on the wax column, which is commonly used, you see the neomenthol and the E-caryophyllene peak, along with the terpenine 4, all very closely eluting. But as you can see, they're all well resolved on the ionic liquid phase. So that's one of the advantages of the ionic liquid phase, giving you some unique selectivity for the analysis of things like peppermint oils or spearmint oils. Here's some work that was done by Carlo Bicchi and his group at the University of Torino, where he was, again, looking at the unique selectivity of the ionic liquid phase relative to traditional phases. And you can see, comparing the SE52, which is a very nonpolar column, 5% phenyl, to a PEG phase compared to the SLBIL60I, where we almost get a group separation of the various compounds. The hydrocarbons, the alcohols, the ketones, the acids, and the dialcohols all tend to elute as a group on the SLBIL60I, well separated, whereas there is some overlap or no separation at all on the SE52 or the PEG columns. Again, this was a vetiver oil. Looking at some other unique separations, these are santalol and farnesol, two typical markers for the authenticity of something like a sandalwood oil. And again, you can see the improved separation of the farnesyl and santalol isomers on the SLBIL60 relative to minimal separation on the 5-MS or the PEG-type phases. In fact, this is again more work done by Carlo Bicchi's group, where they were using the SLBIL60I to determine what are the authentic samples of the santalum or sandalwood oils, and you can see the differences in the standard mixture versus the santalum album spicatum and a commercial santalum album. I don't know the specifics of what were the ones that were adulterated, but you can easily see what very good resolution of all the santalol and farnesyl isomers, so you can easily pick out if something has been adulterated with another oil. We also wanted to look, as I said, we've improved the inertness of the ionic liquid phases, so we want to look at some other compounds that are fairly reactive, a lot of hydrogen bonding. So we decided to look at some creosol isomers, and here's 3 different orthometaparacreosol on the ionic liquid phases. Again, 160 degrees isothermal, the 60 meter, SLBIL60I 30 meter column. You can see very good resolution, very good peak shape for the 3 creosol isomers on the SLBIL60I. Again, orthoparameta separation. Here's the 76I under the same conditions, orthoparameta, so no real shift in selectivity. If we'd have some alkane markers, we'd be able to show some differences in the selectivity, but very good separation. We also looked at some xylanols. Again, a little bit more functionality, something different, some other isomers. Again, isothermal analysis. And you can see good resolution of all 6 of the xylanol isomers on the SLBIL60I. Good peak shape, easily quantitated. Here's the 76I, slightly different elution pattern. As you can see, peaks 2 and 3 are a little bit closer eluting, but still baseline resolution of all these xylanol isomers. Another thing that we've looked at, and this is something that's ongoing with some of the ASTM committees, is looking at oxygenates in gasoline or oxygenates in ethanol. So what we did is a comparison of the SLBIL60I and the SLBIL111I for eluting other oxygenates in an ethanol sample. Again, very good peak shape for the ethanol peak. Well resolved, easily quantitate some of these other oxygenates in ethanol, so that's ethanol. Here's an example with methanol as our main solvent. Again, looking for the oxygenates in methanol, and again, well resolved. And again, these are just conditions, just isothermal analyses, 40 degrees C of these standards that I just shown you. Now, shifting gears to some other specially tested columns, the SLBILPAH. This is a column that we developed specifically for the analysis of polynuclear aromatic hydrocarbons. pHs, of course, are everywhere. They're in all kinds of matrices, soil, water, tissues, foods. When we do them, there are some isobaric type of separations that must be achieved because they have the same mass spectra. So phenanthrene and anthracene must be chromatographically resolved. The benzoanthracene, chrysene, triphenylene, cyclopentacd-pyrene, and then the benzo-BJK fluoranthenes are all typically have the same spectra, so they need to be chromatographically resolved. So to develop a column for pH analysis, we have to have the column that must resolve isomeric sets, must have a high maximum temperature to be able to elute the heavier pHs, low bleed for the mass spec, and then reduce that analysis time for very high throughput applications. So your traditional phase for doing this analysis is either a 5% phenyl or a 50% phenyl. Again, these are the most widely used phases. Use a nonpolar set. Here's 2 examples of the 5-MS phase. One slide, column A, figure A shows us with the polysiphenylene backbone, the arylene phase, and then your traditional 5% phenyl phase on the right. And here's what the analysis looks like on your 5% phenyl phase. You get about baseline resolution of phenanthrene and anthracene, no separation between the benzo-BKJ fluoranthene, and then peaks 15, 16, and 17. You can see coelution between 15 and 16. That's your 5% phenyl phase. And here's what they actually look like in terms of those key separations I just discussed on the 5% phenyl phase. Now, when we shift to the SLBI pH, I mean, this is a story we could tell. It would be one separate talk, but this is basically what we went in and optimized with the SLBI pH phase, looking at different ionic liquid phases, looking at length of the column, looking at film thickness, looking at carrier gas. So what we're able to do is develop a specially tested column that will resolve all these pH isomers within about 15 to 20 minutes. Again, baseline resolution of all these components, and I'll show you that on the next slide. You can see baseline resolution of the anthracene phenanthrene, the only column that's capable of separating baseline all three benzo B, J, K fluoranthenes, benzoanthracene, the triphenylene, and the cyclopentanediene, very well resolved compounds. So it's, again, a specific ionic liquid phase designed to get guaranteed separation of these specific isobaric isomers. Next one, a specially tested column, is the SLBI D3606. Again, this is the D3606 method is actually an ASTM method that is the EPA regulated method for analyzing benzene and ethanol and gasoline. It requires a 2-column backflux system in the current version, and you must be able to resolve benzene and toluene from any other alcohols. So what we did is we got involved in a round robin study a number of years ago, and basically what I'm showing you is the standard that was used in that particular round robin. And you can see a very good resolution, very good peak shape of ethanol from benzene, also very good resolution from MIBK and propanol, and toluene and isobutanol. So all very good peak shape, easily quantified. And here's just some example where we're looking at reformulated gasoline with the D3606 oxygenates on the SLBI D3606. Again, peak 4 is benzene, very well resolved. Looking at some of the other oxygenates in gasoline, and then again, you can easily see toluene and some of the other aromatic compounds in gasoline, so easily resolved on the D3606 capillary column. Again, peak 3 is ethanol, a good peak shape, or resolved from benzene. Now, one of the other advantages of the ionic liquids we talked about is mass spec background and thermal stability. So I'm going to talk a little bit about GCMS bleed on these columns. And here we were doing a comparison between the SLBI-60I, a wax column, and a PAG column, polyethylene alkyl glycol. And basically, we just wanted to look at what is the background on a mass spec with these particular phases. It's fairly well known that wax phases tend to bleed very badly in a mass spec. So we wanted to see how would the IL-60 ionic liquid phase perform relative to the wax and PAG columns. And you can see we stress the ionic liquid column a little bit more, taking it to 280 degrees C, whereas the wax and the PAG phase, we are only running them up in our analysis to 240 and 220 degrees respectively. So here's what the blank looks like of the SLBI-60I. Very low background counts, very little coming off of the column at 280 degrees C. Here's your wax column. Again, a lot of material coming off that column, a lot of background. You can see a huge number of background abundance counts on the wax column. And again, we're only going to 240 degrees C. And then the PAG column, where we're going to only 220 degrees C. Again, a lot of material coming off in this blank run on a polyalkylene glycol column. So to compare all three, again, the wax is in the purple, the PAG is the turquoise, and the SLBI-60 is the black line. Again, we're comparing 280 versus 240 versus 220 degrees. So it easily shows that we can utilize the SLBI-60I with similar polarity to a wax phase or selectivity to a wax phase in a mass spectrometer with very low background. So we can get good quantitation and good performance of that column in a mass spec system. So with that, I'm coming to the end. What I've shown you, ionic liquid capillary columns, are something totally new and different in the world of GC phases. They offer a polarity not achieved with traditional phases, even exceeding that of TCEP. They have better thermal stability than traditional polar phases such as PEGs, cyanosilicons, and TCEP. Have a wide variety of interaction mechanisms. This translates to different selectivity options for these particular stationary phases compared to traditional phases. We've talked about the water columns that provide quantitative analysis of water and other small organic compounds. Talked about the I series. They offer improved inertness while retaining the unique selectivity of the ionic liquid phases. And again, we've shown that the ionic liquid columns can be used in a GCMS system with minimal background compared to PEG-based phases. Again, infinite possibilities in terms of the selectivity of the ionic liquid phases. Again, I want to acknowledge people that we've worked with over the years. This is actually a picture of Penn State University, where we're located about 17 miles east of that in Bellefonte, Pennsylvania. And acknowledge again Dan Armstrong and his group at the University of Texas Arlington, Luigi Mondello and his group at the University of Messina, Carlo Bicchi and the group at the University of Torino, Pierluigi Del Monte and the FDA. I did a lot of fatty acid methyl ester work with Pierre. Lindsay Shearer, when she was at VUV, did a lot of the quantitation with the vacuum ultraviolet system. Again, our R&D staff and many customers worldwide. And again, I want to thank you for your attention. And with that, I'd be happy to answer any questions. Thank you.